Hey everyone, welcome to this video. Today we're going to be talking about something called states of matter and a related concept called state changes. And these are both very important when it comes to thermal energy and specifically how thermal energy interacts with the world and with molecules and with substances. Now this is going to involve a couple different charts and kind of a lot of complexity, so hopefully this video will break it down into things which are simple enough to understand. So we're going to start with a diagram that I've actually pre-made here, but I haven't really labeled yet. And this here is the heating graph of water. So water is a really useful thing to just use as a simple example because water has really well-known melting and boiling points. And these are 2 points we care about. Melting, the melting point, and boiling, the boiling point. And the boiling point and the melting point are important because they're the points at which states change. And I'm going to explain a little more about this in a minute, but we know for water that the boiling point of water is 100 degrees Celsius. And the melting point, which you could also call the freezing point, it's kind of the same deal, is 0 degrees Celsius. And this is very important to understand. So let's take a look at another diagram here. This is states of matter and state changes. So there are 3 states of matter, we've talked about this before, solid, liquid, and gas. And this chart here, which is very useful, shows you all the possible transitions between those states that can occur. So usually we deal with these 4 inner transitions: melting, evaporation, freezing, and condensation. And those are transitions like one step, from solid to liquid, liquid to gas, gas to liquid, liquid to solid. You can also technically have solid to gas and gas to solid. They're called sublimation and deposition. They're definitely much more rare, and you're probably not going to encounter them, but good to understand them that they are there. Now, any change between a solid or a liquid, either way, is called fusion, and any change between a liquid and a gas, either way, is called vaporization. So evaporation, condensation have to do with vaporization, melting and freezing have to do with fusion. That'll become important in a moment. So since we have solid, liquid, and gas, and we know that in order of temperature, solid is the least amount of thermal energy, then you have liquid with the mid amount of thermal energy, and with the most thermal energy, you're dealing with gas. And so, when we have 3 states of water, which is ice, what we would just call water, which is the liquid form, and steam, these are the 3 forms of water. Ice is obviously the coldest. When we hit this melting point, or freezing point, whatever you want to call it, of 0 degrees Celsius, it changes into water. Or vice versa, if we have water and we bring it below 0 degrees, it will freeze into ice. Same deal. And over here we have this point, the boiling point, where water will turn into steam, or steam will condense back into water, and that's at 100 degrees Celsius. So this graph over here is graphing 2 things. On the y-axis, we're dealing with T, or temperature, in degrees Celsius. And I have a scale that goes from negative 10 degrees Celsius to 120 degrees, which I picked randomly just for this example. So we're going from slightly below the freezing or melting point up to slightly above the boiling point. That way I get to show you all 3 phases of water. On the x-axis, we're dealing with Q, which is measured in joules, and this is the heat, the quantity of heat. Remember, we talked about Q, quantity of heat, and we dealt with one of the formulas, which is mc delta T, and we're going to look at that in a little more detail in a minute. So let's understand what this graph is showing you. And one of the most helpful things once you've drawn this graph is to label each point. So I'm going to label the points 1, 2, 3, 4, 5, and 6. And this will make it much easier to refer to segments. So if I ever talk about segment 1, 2, or section 1, 2, I mean this section between the 1 and the 2. And same with 4, 5, or 3, 4, or whatever. And I might refer to these using variables. If I'm talking about Q1, 2, I mean the energy that is happening between 1 and 2 on this graph. Okay, so what is this graph showing? Well, there's an important concept to understand here, and this is the kind of the crux of this lesson, and that is that while state changes are happening, while the physical state of the matter is changing, there is no increase in temperature. And so these plateaus that you can see right over here and right over here are the state changes, because when there is a state changing, there is no increase in temperature. When there is no state change, so here, here, and here, you get an increase in temperature, and that's why you see a rise. This is the heating graph of water. There's also a corresponding cooling graph, which would start here and do the same thing, but in reverse, like this. Or you could literally look at this graph backwards, like just start here and go down, in which case you usually want to draw arrows, and that would be like, oh, this is cooling. It's up to you whether you prefer to use the mirror image or just the same image with arrows, whatever makes you happy, but I just like to use the same image because I find it simpler. So, what is happening here? What is the journey of this water? Well, we're starting at negative 10 degrees Celsius. So at this point at negative 10 degrees Celsius, we are firmly in the solid state. So this, in segment 1, 2, we are dealing with solid ice. When we hit the melting point, while the solid ice is going to melt into liquid water. So during this point, while melting is occurring, there is no change in temperature. Now, as temperature continues to rise, we now have the liquid water phase. It's a liquid, and we would call it water. Then, at 4 to 5, we've hit 100 degrees, which is the boiling point. And so now there's boiling occurring, and the water's transferring to steam. And finally, as the temperature continues to increase, now you're dealing with gas, and that's steam. So this is assuming the temperature was just linearly increasing, like or more or less. You're heating up a pan, for instance. We could look at a graph of water if you were boiling some water. We could look at a graph of metal if you're melting some metal. Whatever you're doing, these graphs apply. This is the heating graph of water. You can have a heating graph for any substance just by changing these boiling points and melting point. There'll be a chart that you will have which has the melting and boiling points of all the relevant things of the substances that you'll be dealing with. If at any point you don't know one of these, it'll probably be also given to you on a test. So you should always know these, because this is not something we could calculate in any way. You kind of just need to know the melting and boiling points of those substances. Okay, so this is the heating graph, and we understand this. Now we need to look at what's the practical use of this. And the practical use is for calculations. Let's take some sort of random question that you might be asked, which is, I have a sample of water, liquid water, at 35 degrees Celsius, and I evaporate it into gas, which is at 150 degrees Celsius. How much heat energy was absorbed, released? How much heat energy is there? So if we mark these points, here's 35 degrees Celsius, and here somewhere is 150 degrees Celsius. And so we're concerned basically with this range of motion here. Up here, stopping at 150. And there's a bunch of different lines, and we would need to calculate the total amount of heat along these lines. And we can do this with two different formulas. And good news, you already learned one of these formulas, so it's actually only one additional formula. Or kind of two, but kind of one. You'll see what I mean. So this is the most important thing to understand. When we're calculating overall heat, it's just a matter of adding together the different segments. So here, we have kind of three segments. We could label it A, B, and C. And you would calculate those each separately, each of the straight lines. And so you would say that the total Q is QA plus QB plus QC. If you're dealing with the entire state change spectrum, like from all the way below to all the way above, you could make a statement that QT equals Q12 plus Q23, etc., etc., Q34, all the way up to Q56 and beyond. And this is the most important concept to understand. And now we're going to go through each of these Qs. So there are two different formulas, and the two formulas depend on, basically, is a state change occurring? Is a state change occurring? And what I mean by that is, are we literally in the middle of transitioning from one state to another? Are we at one of these plateaus in the graph? Are we at a point where this is flat? Meaning we're at a specific temperature, either the melting point or the boiling point, and so the state is changing. If we were at one of those points for any reason, what we would need to do is use a specific formula. If we're not at that point, if we're not dealing with a state change, we use a different formula. So we'll start with no because it's slightly simpler. If there's no state change occurring, then the heat is just going up or down. You're either heating or cooling. And the formula we use is one that we're familiar with. Qmc delta T. We did this last time. This is the heat. M is mass. C is the specific heat capacity of the material. And delta T is, of course, the change in temperature. Makes sense. Now, if, however, we are dealing with a state change occurring, we ask ourselves another question. Is it fusion or vaporization? So remember I talked about the state change diagram, and I said, this is going to become important. This is why. If you look at these state changes, you need to be able to see, is a specific state change a fusion or a vaporization? So if you're dealing with solid between liquid, or if you're dealing with liquid between gas. Solid and liquid back and forth is fusion, liquid and gas back and forth is vaporization. So, if you're dealing with fusion, you're going to use this formula. Q equals mLF. If you're dealing with vaporization, you're going to deal with a different formula, but it looks very similar, and that is Q equals mLV. Now, what is these new things? So Q is not heat, is still heat, here, but we call it the latent heat. And that means it's the heat at the flat points of this graph. There's no change in temperature over this time, so it's latent heat. And what is the LF and LV? Well, these are these specific latent heats of fusion and of vaporization. L for latent, F for fusion, V for vaporization. They're on that same chart with the melting and the boiling points, so that you can easily access them when you're doing tests or when you need to know them for questions. And M is just mass, which makes this an even simpler calculation because there's no change in temperature, so that doesn't factor in. And you can deal with heat capacity, C, because that involves changes in temperature. So instead you deal with these latent heat of fusion and latent heat of vaporization. So here's kind of the flow chart. Is a state change occurring? Yes. Is it fusion or vaporization? Fusion, use mLF. Vaporization, use mLV. If there's no state change occurring, use Q equals mc delta T. So back to our original question I had asked, which is measuring the amount of heat between 35 degrees Celsius and 150 degrees Celsius of water. We can take a look at this with a simple approach. Like I said, we know that QT equals QA plus QB plus QC. And if we take a careful look, we can see that QA and QC, there's change in temperature, it's a diagonal line, whereas QB there's no change in temperature, it's a flat line. So, QA is going to use MC delta T. QC is also going to use MC delta T. And QB is going to use one of the other formulas. And how do we know fusion or vaporization? Well, which state change is this? This is boiling. So it's from a liquid to gas, and that's a vaporization. So we use mLV. If we take these, we can create a formula where we say, well, the total heat equals MC delta T, and this is the delta T in A, plus mLV plus MC delta T in B. And now we could go through and say, okay, so what are these specific heat temperatures? And in the case of A, we remember that it's 35 initially and it rises to 100. So we would say, well, it's 100 minus 35, final minus initial, plus MLV plus MC, and the temperature is here in B, while it's, in C, while it's going from 150 and 100, so 150 minus 100. And obviously you could fill in the mass, and the specific heat capacity and the latent heat of vaporization would be found by looking at a chart. And you could then easily solve for that heat. And that's basically the purpose of these graphs. You never really need to do the graph, but boy can it make it a lot simpler to understand what's going on in certain contexts without getting confused by which states are happening or what's going through what state at what time. This is pretty straightforward. Alright, I'm going to conclude with two just kind of extra points that are worth noting. One of them is that this latent heat value, LF and LV, have specific definitions. It's the amount of thermal energy required to either do fusion or vaporization of 1 kilogram of the substance. That's why you multiply it by the mass. That 1 kilogram gets multiplied by the number of kilograms to get the overall heat. So that's pretty straightforward there. And the other point I'm going to mention is just when you're solving these formulas, to watch out, make sure you do the proper final and initial, so you're not subtracting things in the reverse order. And when you add them together, always make sure you keep track of whether you're heating or cooling. You might get numbers which seem to have the wrong signs. You can always just flip everything to the same sign. Make it all the right direction. Make it all positive, and then just at the end, add the word, absorbed or released as needed. Don't worry too much about the signs. Sometimes they'll come up a little bit wonky for various reasons. That's nothing to worry about. This is basically the entirety of how state changes work. And that's pretty much all you needed to know for this video. Hope that was helpful. Thanks for watching.